Thank you for coming. My name is Jeremy. I'm one of the organizers of the Seattle Postgres User Group. The other organizer, Lloyd Alman, is not here tonight. He's out of town, so I'm running the show this time. I will just real quickly do the announcements, then I'll introduce our speaker for the night. Because you're not here to listen to me talk, you're here to listen to Jonathan. So real quickly, announcements. I see everybody got name tags. Thank you. Where are the name tags? It'll help everybody kind of be able to meet each other, see who you are. There's a sign-in sheet in the back. If you didn't sign in, please put your name on the sign-in sheet. That does not have contact information, so I actually can't email you and stuff. That's just for us to have a count and for us to have an idea of who came and how many people we had. If you want to be if you want to find out about meetups, the place you need to go is meetup.com. So that's kind of right now our main place for finding out about future meetups. We also, just on that note, I'm going to mention we have a website at SEAPUG, SEAPUG.org, that we've had since 2009. Lloyd and I are trying to revive this website, so if anybody's interested in volunteering, hit me up after the meetup. I'd love to chat. Bathrooms, if anybody needs them. There's some that are really close right through that door. There's also bathrooms right out in this hallway, just right around the back. Let's see, there's the SEAPUG library. There's a table right there. You're welcome to borrow books. So they're there. If you want to borrow a book, stick your name, put some contact information just on that clipboard so that if the book doesn't show up, I'll come back within a year or so. I'll probably ask you if you're really enjoying it, just to make sure you didn't forget. I might ask you to do a book report if you keep it for that long too. You have to come back and tell us what you learned. There's on the library table, I just kind of like to mention, there's a stack of a thing that I call the happiness hints, which are some sort of good ideas with Postgres. If you're new to Postgres, that's kind of one resource. I like to plug it. It's a little bit of self-promotion. There's also some PGUS stuff on the table by the entrance. So lots of information. Two important upcoming events that I want everybody to hear about. Number one is our annual July barbecue. So every summer for many, many years, we have kicked off the summer with a barbecue, and usually around July 4th. So this year, Thursday, July 3rd, it's going to be in this building on the back patio. You can't see it from where you're sitting, but from where I'm standing, I can look out that window and I see Lake Union. It's a gorgeous patio. It's got a grill out there. We cook burgers. We bring a bunch of food and just kind of have a good time hanging out. So that's going to be Thursday, July 3rd. We've already got the patio booked. Dates on the calendar. Hasn't been posted on the meetup site yet, but it should get up there pretty soon. So mark that. Come on out, hang out. We'll have a good time. And then secondly, this just went up on the website a few days ago. Normally we meet up on Thursdays. Next month we kind of had some complications booking this room. Somebody beat us and they got it, and then we tried, but we couldn't finagle our way back. So we're meeting on a Wednesday instead of a Thursday. Don't get confused. I'm mentioning that because we're always on Thursdays except for next month, and somebody's going to show up on Thursday, and you're going to be so sad because we have an amazing speaker. Gwen Shapiro is coming up from California. She is one of the co-founders of a company called Nile. It's a really unique opportunity. I've heard Gwen speak a whole bunch of times, most recently at the PGConf.dev last year. It was just sort of the big Postgres development conference that was in Vancouver. And she's one of those people who is able to go pretty deep technically, but explain the concepts in a way that's really accessible. And that's a very it's a really valuable skill. So I really enjoy hearing her speak. I think it would be a really great meetup to come to. I'd encourage you guys to come back next month. The startup that she does, Nile, is built on top of Postgres and does this massive multi-tenant scale out stuff. And that's what she's going to be talking about. So that's next month's meetup, Wednesday, May 7th. So you can also, that's already on the site, mark it on your calendar now. Come back here, Wednesday, May 7th, this room, 6 o'clock. It's going to be a really cool talk. All right. So those are all of my announcements for the night. It's time for me to introduce the speaker, which is the actual reason that you're here. Tonight our speaker is Jonathan Katz, who has come to us all the way from New York, right?
Via California.
Via California. Jonathan Katz is a principal product manager technical on the Amazon Redshift team and is based in New York. He's also on the core team of Postgres and is an active open source contributor, including to pgvector. Please give a welcome to Jonathan.
Thank you. Thank you, Jeremy. So first, one shameless plug as well for an upcoming event. If you want to go to that pgconf.dev that Jeremy mentioned, it is coming up from May 13th to May 16th in Montreal this year. And that's where we talk about contributing to Postgres in all different ways, technical, community-wise, etc. But you're probably tired of the shameless plugs at this point, so let's get into the topics. So the title of this presentation, Jeremy asked, well, two things. Like first, what's the title of the presentation? And asked me for about a month before I gave it to him. But I asked ahead of it, what kind of topic do people want to hear in this space in terms of vectors? Do you want a best practices talk? Do you want an internals talk? What would you like? And the survey came back, it was 50-50 split. So this is going to be a little bit of everything. There's going to be a lot of ground to cover, and we're going to go back and forth between use cases, best practices, but why are we picking these best practices? So sort of the proof is in the pudding. And the way I like to start with the presentation is, why do you even care about vectors in databases? Like vector is like such a fundamental mathematical concept. Typically you learn about them in physics class or you learn about them in Comp Sci 101, and then you kind of forget about them except, well, we always deal with arrays, but vectors are a funny kind of array. And as we're going to go through this tonight, we'll first talk about like why this matters. Hint, it has to do with AI, and generative AI plays a very large role in it. Then how Postgres can be just as good of a vector store as anything out there. And we'll see this through the pgvector extension, through some different strategies and best practices, and then briefly on the roadmap. This is going to be a long presentation. We're going to cover a lot of ground, but again, through each step, we're going to, I'm going to do my best to explain like why everything matters in here. And first, I just really want to start at the high level, and with an example where that brings the vector into generative AI. And the first thing is maybe a simple example. Who's ever had to purchase car insurance before? Yeah, exactly. And imagine that you're building a generative AI application, because it feels like this is something that is a transaction that we can automate. And you go in and you say, I'm interested in getting car insurance. And the generative AI agent comes in and starts thinking about it. But it's like, wait a second, like there's a really good opportunity here. Like, is this either a general Q&A type question? We're going to give general information about car insurance and its regulations. Or is this like very specific? Like, do I know this is Jonathan coming in to purchase car insurance? I know his driving history. I know how many speeding tickets he's gotten going to pgconf.dev. I know like all this information to like derive this. So how do we get that personalized information into these generative AI models? Because you've probably heard that building a generative AI model, also known as a foundation model, can be very expensive. You need fleets of GPUs. And sure, we're getting faster and faster, but you might not be able to purchase a fleet of GPUs. And yet we can make generative AI accessible to bring data resting in your private data sources, databases into generative AI. And the common technique to do this is called retrieval-augmented generation, or RAG. How many folks are familiar with RAG? Show of hands. Cool. And what's great about RAG is if someone comes in with a personalized question to a foundation model and it doesn't have the information about it, the foundation model is like, nope. But if you do have that data existing in a database, you can basically augment the foundation model as part of the prompt that goes into it. So the prompt is effectively, think of your prompt in some ways as a SQL query that you put the prompt of the foundation model, and the foundation model gives an answer in the form of some rich form of text. And when you do that, you get that personalized response that you might see from these AI models. Really, it's kind of simple at the outset. We're going to drill a little bit further in terms of how we pull it together. Because in RAG, there's two types of data that go in. There's situational context, which are facts about the situation. So Jonathan's driving history, Jonathan's speeding ticket going to pgconf.dev, what car am I buying, where do I live, etc. And those are all facts about the situation I know by the person asking the question. But then there's semantic context, which is what gives the meaning to the situation, such as regulations about driving in Washington State, car photos, claims that have been uploaded in text. In some ways, you can think about this part as structured data that exists in, again, you can see this was a reinvent slide, but it exists in your databases. It's facts that already exist there, your data lakes, etc. Could be semi-structured, and we don't need to go into that. But semantic context is, again, this is where the meaning is coming from, and it's that unstructured data. So we need a way to be able to take that unstructured data and give it some kind of mathematical representation, wink, wink, vector, to be able to derive that meaning. Now, before we get into the role of vectors in this, one thing that a lot of questions I've had over the past couple of years about bringing data to generative AI is, Where does the context come from? Where does the data come from? I just want to touch on this real quick because a lot of the work you're going to be doing here is just traditional data processing. It might just be you just bring in a SQL database and run queries and take the results and put it into that text-based prompt and ship it off. That's a lot of the work in many ways, and it might look like your general architectural diagram. And again, we're not going to go through all of this here. I have a separate presentation for this. But part of the point I want to make is that a lot of the work you're doing is all the same as you've been doing before. There's this new generative AI thing and these foundation models here. But we do want to understand how those work, particularly around semantic context. And that's where we need the mathematical structure. And this is where the vector comes in. So within AI, there's a specialized model called an embedding model. And the embedding model is able to take unstructured content, documents, audio, video, images, whatnot. It's able to find the meaning in it. And again, different models have different specializations. Some are for text, some are for videos. But through how they've been trained, they're able to see the relationships between words and images and say oh, this is a cat, your vector and vector space is here. This is a dog, you're over here. This is a turtle, this is a closet, right? It's all, it's able to make those determinations. And from there, you can determine how similar you are and how different you are. And that's the fundamental operation in vector search is, what am I most similar to is the query that you're doing all the time. We'll see an example query in 2 slides on that. But first, let's understand the flow. So how are vector embeddings used? There's 2 parts of the process. First, you have to take your raw data, turn it in, and at some point you do need to transform it. That process is called chunking. We're not going to get into that here. But the chunks are basically pieces that fit into the embedding model. The embedding model is able to do the processing on the chunk, figure out the relationship, turn it into a vector, and you store it in a database. So that's part 1, this ingestion. Then part 2 is, you can call it the agentic part, you can call it the Q&A part, but something comes in from one of your users that, it might be a question, it might be a comment, it might be a statement. You take that, you turn it into a vector embedding, and then you find the chunks that are most similar to it, again, by doing that similarity search. So once that occurs, you smush it all together, you have your semantic context, your situational context, you send it to a foundation model, you get that personalized response. Yes, Jonathan, based upon your driving history, your car insurance rate is, whatever it is. And this is all you got to do, kind of. This is an example of vector search query. And, effectively, it's select that data, really. In this case, you're looking for that text chunk. Then we calculate the vector distance here. So you have a vector, you have your embedding, and we want the shortest distance. That's the order by the distance, limit 10. So you might be familiar with this from geospatial queries. It's all the same. But, and also keep in mind, geospatial is 2D and 3D vectors. They're very small, and there's actually some very efficient search techniques for this. But for these larger vectors, there's a problem. But maybe not a problem, but there's challenges. First, it takes time to generate the embeddings. So you might not want to do this on the fly every time. Again, it depends on your system, but you probably want to store these and have them cached, because if it takes 100 milliseconds to generate an embedding, and you have 1 million of these things, you can't generate the embedding every single time. The other challenge is that I just mentioned geospatial embeddings are 2 to 3 dimensions. Sorry, geospatial vectors are 2 to 3 dimensions. But you see a lot of these embedding models, they're 1,000 dimensions, 2,000 dimensions, and that's a big payload. And this matters because when we think about the data typically going to Postgres, it's less than a kilobyte. It's probably, the rows tend to be very small. But here's a payload that's 6 kilobytes. And if you have 1 million of these, this is 6 gigabytes. And again, I was running a production database for years. It took 3 years for me to have 6 gigabytes of data, within that database. And here, 1 million rows, boom, 6 gigabytes. And you think you can compress it, but you can't. Because you can't really compress a bunch of random 4-byte floats, because that's effectively how a vector looks like. There's techniques to shrink it down, which we're going to talk about later in the presentation, but there's trade-offs with that, particularly around the loss of information. And then there's no shortcuts, because when you have to query a vector, you have to query every single dimension, unless your embedding model says you can stop after, let's say, 256, but that's still 256 computations. Now, the other thing is that when you're doing a nearest neighbor query, you have to look through the entire vector space in order to figure out who are your exact nearest neighbors. So just take this example of 1 million vectors that are 1,500 dimensions that you have to compare. That's a lot of computation time. The good news is that some folks have been looking at this for, I'd say, about 25 years in terms of how do we accelerate computations on modern vectors. And a technique that's emerged is called approximate nearest neighbor search. So the idea of exact nearest neighbor search is what I just described. You have to compare every single vector to find your point. And with like 2 to 3D, there's like very efficient techniques. But again, it's the same principles. We want to be able to find our most similar vectors without searching for all of them. And yes, if you only search for like 1,000 vectors out of 1,000,000, it's going to be faster. But there's a trade-off because we might not see all the best candidate vectors. So there's a measurement that we have to worry about here called recall, which is your percentage of expected results. So let's say we're doing a query, and these are like the 10 nearest neighbors that we expect to get. But we only return 8 out of the 10, and we return some other 2. Our recall is 80%. Now, as you go through evaluating your vector search systems, be it pgvector or something else, what you always have to keep in mind is your recall and how much that matters. For example, if you're doing something where you need to visit all the best candidate vectors, like a critical, maybe something in healthcare where you don't want to mess up, you're going to have to do an exact nearest neighbor search. But based upon how much you're willing to trade off having the best results, you can get faster in your search, but you're going to have that recall trade-off. Now, as you start evaluating vector storage, and we're going to go very deep into one particular vector store today, these are all the factors that ultimately impact everything with it, like the cost, the performance, how much storage you need, what your instance size is, what your database size is. And really the root of the decision making is not cost per se, typically cost will be a big deciding factor, but it starts here. Your embedding model, your foundation model, and what problem you're trying to solve. Because if your embedding model is 1,500 dimensions, that might make some of the decisions around storage that we're going to talk about. If it's 64 dimensions, again, there's going to be other decisions you make around that. But in some ways, it could be limiting. If your embedding model is 65,000 dimensions, there's going to be some challenges using that within Postgres today, unless it's a sparse vector. But we're not going to talk about sparse vectors. But all these things matter, and they're all in tension with each other. And this is kind of why I call vectors a nasty data type for databases, is because you can't really have these all without leaning into it. So for example, if relevancy matters to you, well, you might have to spend more on your database to be able to do more exact nearest neighbor searches, because those are very CPU intensive, and that's going to sacrifice performance if you're in a high throughput system. Again, we'll weigh off some of the strategies as we go through this talk, but these are the items that will always be in tension. Finally, the part I love nerding out about is how do you actually measure the effectiveness of a system? There won't be a quiz on this, but I do want to point out when you read blog posts about everyone saying oh, I have the fastest vector search, certain things you got to look for. It's all anchored by recall. If there's no recall measurement in terms of what you're talking about, it doesn't have any meaning per se. Because I can tell you one time I was playing around with a new pgvector algorithm, and it was the fastest search I ever saw. I was getting 7,000 queries per second on a single connection, and the recall was 0%. Basically, right? But I'm oh, cool, it's so fast. But yeah, no, recall matters. And the other two things you look at are your index. In particular, how long does it take to build the index, and how big is your index? Because we're going to see that these indexes are quite large and can take a lot of time to build. And the trade-off in that might be that your query throughput and latency is amazing, high throughput, low latency, spending more time on the index build, or maybe I'm okay to spend more time on querying because I don't want to saturate my CPU with the index. Again, all these are in tension, and as you make the evaluation, particularly as you scale up, you will need to consider that. So that's setting up the general problem. Now, how about Postgres' vector store? So who knew that you could use Postgres to store vectors? Who knew that you could use Postgres to store vectors since 1986? Because arrays were part of the original Postgres release, because arrays were used as a shortcut to be able to store access control privileges. Now, you'd have to add the distance functions to the arrays to be able to do that comparison, but that's actually kind of a fun fact. Postgres has done vector search effectively for about 40 years. Now, maybe I should have led off with this. Who's using Postgres today? Okay. So why even consider Postgres for vector search or using a generative AI? Well, the general pitch on Postgres is that it's a vibrant open source community. It's been around for almost 30 years. It's been developed for almost 40 years. And really a lot of the original attraction, at least for me, was that it was great. I was an app developer. There was so much functionality in it. I was building out apps on it. And a lot of the work in Postgres lately has been more on scale, availability, and being able to support bigger and bigger workloads. Now, the other thing about Postgres is that, by design, it's extensible. And that, again, that goes back to the original design when it was a Berkeley project, that you could basically add capabilities to Postgres without forking it. Like, there's thousands of these extensions. And one of them, built in 2021, was called pgvector, which added vector search to Postgres. And what's nice is that there's a lot of tooling already available for Postgres. And one of the early appeals for people to prototype Gen AI applications on Postgres was, I already have my Django framework or my Rails framework, or LangChain already has a Postgres adapter. Let me just start building on top of that. And that just made it much easier to start building. And sure enough, pgvector continued to add features to help with scale, which we'll talk about. But one thing I just want to drill into real quick, I'm not going to go through all of this, but Postgres is ACID compliant, meaning there's certain guarantees in terms of how your data is stored and how it's visible. My favorite of this is the last one, the D of durability, because basically you say, like, when I've committed a transaction, I know it's stored to disk. That's a very important property that indexing systems may or may not have, depending on what you're doing, because there is some overhead to ACID, but that's fine. You know that your data is stored with integrity. So whenever, and I'm saying this like beyond just using Postgres for vectors, like this is just a general point that you should care about durability when you're trying to store data. Now, pgvector. So as I mentioned, Postgres has thousands of these extensions, and there's one called pgvector. Fundamentally, what pgvector does is it adds vector search. For vector search, you need a vector data type. And pgvector actually has a few different ones of different sizes. You need distance operations. So there's Euclidean distance, which is like line of sight. There's cosine distance, which is angular distance. There's inner product, and of course, I'm from New York, so Manhattan distance is very important to me. That's block by block. Now, the other thing is that there's indexing methods as well, which we're going to spend a lot of time on, because the indexing methods give the approximate nearest neighbor search. I'm going to lean in a little bit and also say Postgres has all the other features of Postgres. So it's not just pgvector, there's Postgres and the other extensions you have. So you have regular indexes and specialized indexes in Postgres. And what we saw with pgvector was kind of what I was alluding to before, that when generative AI became popular, people were using it because it's in Postgres, it's there, I can rapidly prototype, it works with all my tooling already. But at that time, it really was just that. Like, it needed more work to be able to scale further. And by 2024, a lot of those features were added, that you could get very fast vector searches with high recall rates. It could support larger vectors. It could support smaller vectors through quantization. And there's much better support across just wider variety of developer tools. Really rapidly, just in terms of like everything that's been developed, we're currently on pgvector release 0.8. So 0.4 is when it really started gaining popularity, and in that release it was fundamentally working on one type of index. The next release added the HNSW index type, which we'll spend most of this talk on. Then after that, it was speeding up HNSW builds because we saw larger data sets coming in, and we don't want slow index builds. Then it was, okay, we're getting like really large data sets. We might want to leverage a technique to shrink the vector size so we can store more data and possibly accelerate searches. And then finally, the other area we're going to spend a lot of time tonight, which is, I actually call this, do we actually need a vector index? Because we're going to see classical indexing techniques might be just as good for some of these vector searches. So let's say you've installed pgvector. How many people have installed pgvector? Cool. So if you install pgvector and you see like, okay, I'm reading the docs, because how many people read the docs? That's a general question. Like, read the. By the way, like when I first try things out, I don't read the docs, and like I got very confused because pgvector is not returning the results I expected because I didn't understand recall. But there's two methods in pgvector for indexing. There's IVF flat. IVF flat is a clustering method, and the idea with IVF flat is you have your set of data in here, and you say, okay, build me like 5 clusters. So there's an algorithm called k-means, which k-means is actually like an NP-hard algorithm. So so you have an approximation algorithm which says, all right, find me like the 5 centers within the within the audience, and then build links between them. What's cool about that method is it's actually very fast, and if you build small enough groups, you're going to be able to do some very fast indexing. But typically, you need to build larger groups to get better recall in them. And there's some, you also need to have all your data like already available. So it's a little bit harder to use, particularly as someone who's been an app developer. But like for cases where IVF flat works, it works well. But we'll spend most of our time on HNSW. So HNSW stands for Hierarchical Navigable Small Worlds. It's hierarchical because you're going to see like we have layers of graphs we're going to search through. The original paper was just called Navigable Small Worlds, and it actually wasn't as good as adding the hierarchy, which we'll see. But the idea is that you build a graph. So every time you add a vector into the graph, you're going to be pointing at like a bunch of other vectors around you. You're saying like, hey, these are my closest neighbors. So as I go through the graph, the idea is you're going to be around like your best set of neighbors. So you don't need to search like all 1,000,000 vectors. You only need to search like 2,000 and you get like a very good response. The other nice thing about HNSW is if you're a traditional app developer, it feels like just using a regular index. You insert data, it adds to the index. You insert data, it adds to the index. You delete data, it removes from the index, et cetera, et cetera. And you don't need to think about it too much. We're going to think about it a lot tonight because we're going to look about how we got to like the best practices and recommendations for pgvector. But through that, you'll then be able to know how to evaluate these things. So one more cheat sheet before we really dive in and get to the really the internals and how we came to these recommendations. So we've talked about exact nearest neighbor search, approximate nearest neighbor search, and 2 different indexing methods. Which ones do you choose? If you need exact nearest neighbor search, you don't choose any of these. You just grin and bear it. You do these massively parallel vector computations and hope for the best. Spent on CPU. If you need just fast indexing, IVF flat is the way to go. That means you already have your data set available. You just need to get an index on it, and you understand the properties of the vectors and how they're related. This is almost the one that it takes a lot of work to do, but if you get it right, you get it right well. I put an asterisk because the parallel builds for HNSW are actually pretty fast now. Like not as fast as the IVF flat parallel builds, but fast enough. If you want something easy to manage, HNSW. And by the way, like you see HNSW is, it seems to be the most popular of the vector indexes because it's just very easy for folks to manage. It also has this high performance recall ratio, which people like getting, highly relevant results very quickly. But the thing that's kind of the hot topic in vector search, which I'm actually going to present tonight as a boring topic, is filtering. Filtering is the where clause. Basically, I'm trying to do like additional selection on my data. If you have high selectivity, where most results are filtered out, we're going to do an example of selectivity later. Don't use a vector index. Use like a classic index, and we're going to see why later on. If you have low selectivity, which means that you need to search over, your filter eliminates like 1 out of 10 rows or even like 1 out of 100. Well, oh, sorry, I did that in the wrong order. If you're not eliminating a lot of rows, then yes, a vector index works very well here. All right, still with me? Cool. All right, we're about to like dive very deep in. So this is for the the 50% of you that really want to go into it. We're going to focus on 4 areas of pgvector tonight: storage configuration, this HNSW index, filtering, and quantization. And actually, I think that's in the wrong order. I think I did quantization before filtering. So that's an example of bad recall. Now, storage matters. Like what was fun to me is like I'd used Postgres for nearly 2 decades. And some of the things that we're going to talk about here, like I never even considered, because again, a lot of what you store in Postgres is like small data. Like, even with JSON, like JSON, you might be storing like kilobyte payloads, which like, fits into a page pretty well. But again, like another thing is like, I never really thought about pages. Then that's kind of shocking, right? Like Jeremy said, like I'm on the core team of the Postgres project. And like here I'm saying like, I never thought about like a page, but the thing is like the page is the atomic storage unit for Postgres. Like when you think about storing data, you might think about you're storing a row and like, you have 5 rows in it, but it's all going into this unit that's 8 kilobytes by default. And again, having the page is very important just in general database management. We're not going to go into that. But what I want to call out is that we're going to see that because these vectors are so large, they take up large portions of the page, but in a way that's not optimal, where we end up with wasted space. And this is kind of frustrating. At least for me, I find it frustrating. So for example, I don't expect you to memorize all this, but you look at these different sizes of vector dimensions up to like the max that'll fit on a single page. And we see that as we go through it, that when our vectors are small, yeah, we can cram a lot of them onto a single page, which might seem nice depending on your search pattern. But right around like 1,000 vectors, sorry, 1,000 dimensions, we can only get one of them on the page, which leaves us with 4 kilobytes of wasted space. And that's just like, it's almost better to have like that larger vector on the page because there's less wasted space. And again, like, is this a problem? I think that's a good discussion. It's actually something I'm gonna bring up next month at pgconf.dev. I've already like flagged it as something to think about. But the reason I bring it up is like as you're doing capacity planning, like, and you're planning to store like a lot of vectors, I'm talking about like 100 million, a billion, etc. Something to consider. Like you will have some wasted space. The other thing is that, you might say like, oh yeah, well, I'm not using a managed service. I'm self-managing Postgres. I can recompile the Postgres binary and, create larger pages. I think up to 32 kilobytes. And that's actually really good. I see Mark here. Mark's done some testing with like larger pages and seen like much more efficient, ingestion patterns. But the index pages are not resizable. Like they're actually hard coded to be 8 kilobytes. So even if you resize the table pages, which is known as the heap pages, you can't resize the index pages right now. And apparently it's actually a pretty big project. I was talking to one of the committers about it who was like intrigued, but like it's a lot of work. It's not just like flipping like one thing in the code. Now, the other thing is like, you might say like, oh, wait a second, like I've heard of this thing called Toast. Who's heard of Toast? Cool. So Toast is a way, it was actually designed probably about 25 years ago as a way of handling larger data, because you probably said like, wait a second, I've stored really large documents in Postgres before that are megabytes. So yes, this is called out-of-line storage. And what's interesting is that, Postgres, by default, it's going to toast values over a certain size. Again, you're probably not even thinking about it until you run into issues here. And the reason you typically don't, think about it is we'll see like it's not on your hot path. You're typically doing an operation after on the data, retrieving data. There's a few different storage types in Postgres. I'll go through them real quick. So you have plain, which is basically all the data stored within the page on your table. You have external, where if you hit the toast threshold, you have a point, you store some of the data on the table, you point to your toast table, which has like the additional data. And you have extended, which is the same thing, but then you also compress the data, which like, again, if you're storing text and blobs like that, you do want to compress it. But just a fun fact, so pgvector before version 0.6 used extended as its default and then switched to external because, again, you can't compress a vector. You saved like 5 to 10% on CPU. So instead of me trying to like do a pointer and explain all of that, let me show an image. So like this is like plain storage. So I have a big vector. It's stored on the page all in line with the rest of my data. With Toast, most of the vectors stored in an external page. So typically, Toast is a good thing. Again, for those of you who have had issues with Toast, we can talk more. But the idea is that when you think about like large text data or maybe large JSON documents, you're probably not searching inside them, or you're doing like a post operation. Most of the search is going to be on the main data within your page. So it doesn't kind of matter that it's like on a separate page because you're not doing that much work on it. But this actually impacts vector search, because vector search is on the hot path. Like it is like computationally intensive operation. And you're actually doing both your filter and your ranking on this vector search, because at the end of the day, it's like I need my 10 closest vectors to me. I need to be able to access that data quickly. And what's interesting is that it actually impacts speed. So I don't expect you to read like all the numbers on here, but I wanted to point something out, that when we hit the automatic toast threshold, which is again above whatever that, like 510 dimensions, we see that our toasted data, which is this one, we drop like 4x, in terms of like our query time or our query throughput, because we have to do more work to go from heap table, toast table, heap table, toast table. And I do think there's like an inefficiency here. Again, I've been like floating this with some of the Postgres committers, say like, hey, I feel like we can do better here. But for now, like it is something to consider. Like if you're doing the exact nearest neighbor searches, like you have to pay a penalty here. If you're, with indexing, you might not see it as much, because again, if you're searching the index, there's no toast, so you're always going to have, better results. But if you're constantly having to go through and do operations on your table, and you can afford to have it in plain storage, it might be better, because you will get that better percentage. The other area it impacts exact nearest neighbor search is query planning. Like this is a real problem. So let's take that smaller vector that fits on a page. That this was like 10. Like find me like the 10 closest vectors in 10 million rows. So search all 10 million rows. There's 6 parallel workers planned. Cool. Same exact query, 1,500 dimensions, 4 parallel workers planned. That doesn't make sense because this is definitely a lot more data. This is, like 10x more data. And that's the impact of, oh, maybe it was the next slide, hold on. That's the impact of here, because Postgres Parallel Worker Planner is looking at that page and saying like, oh, there's not that much data here. I don't need as many parallel workers. I've actually brought that up because that is an issue. Now there is there's an escape flag there, which is this thing min parallel table scan size. So if you read really deep in the Postgres documentation, or if you see the pgvector README, this basically determines like when to and how much to do a parallel scan on. So if you set it to like the bare minimum value, which is like I think 1 kilobyte, you get the expected number of parallel workers. Now, why am I bringing this up? Because you're probably going to use approximate nearest neighbor searches anyway, or something else. Well, maybe you won't one day. Like maybe you need to do that exact nearest neighbor search, or maybe you're seeing some like slow ingestion times, or it's taking a while to rebuild your index. This is why. So things to think about. If you're really performance sensitive and your vectors fit within a page, use plain storage. This is the command to do that. This is the slide to screenshot. And this min parallel table scan size parameter, which you've probably not heard of, can help induce more parallel workers. But again, you gotta be careful. This isn't like for everything. Like this works really well for vector search because vector search is so computationally intensive. Like you do want the parallel workers to get that extended parallelism. So now the really deep part of the talk, and I realize it's already 7:20, so I think we'll do it at a good pace. So HNSW, this is where you're going to spend most of your work, and hopefully not, because you're going to use these recommendations, and these are pretty good. So there's 2 index build parameters in HNSW. There's M. M is the number of bidirectional links, and pgvector defaults it to 16. Like different implementations of HNSW have different recommendations. For pgvector, we determined 16 was best based upon the algorithm used. So M is the number of, so if your M is 16, then basically you're saying I will have up to 16, pointing 16 vectors around. EF construction is your search radius as you're building out the vector index. So basically what you're doing is you traverse the graph, you're keeping in effectively a short-term memory of like, here's like the best vectors I've seen as I've gone through the graph. And it's a list of 64. And it's basically the list of vectors I'm going to keep visiting until I've converged. Like this is a graph, a graph algorithm. Eventually it's like, oh, I've seen like everything within this neighborhood, like I can exit. So it defaults to 64. If you're interested in how we got to 64, you can go to the GitHub repo. There's a very lengthy GitHub issue on it. I used to recommend 256 once parallel HNSW was in, because we'll see that's where we got to diminishing returns. But there's actually like a slight QPS, queries per second hit, when you use 256. I'm seeing it's really around like 5 to 10%. So this is why it's like, well, maybe start with 64, and if you're more recall sensitive, go to 256, but note that you might have a slight performance degradation. Similarly, EF search, so the thing is like, you're probably going to use the default parameters, and like these will be fine. Like use 1664. If you don't have an issue, don't worry about it. EF search is probably the one you're going to end up tweaking. So EF search is the flip side, is when you're actually doing that select star from table, order by, blah, 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 limit, blah. This is going to determine like how many vectors, it's the radius of vectors you're going to search. And we'll see an example of that. This defaults to 40. Previously, so pgvector kind of like set this up because the most common query was limit 10. And unless you had to go beyond limit 40, EF search 40 was fine. This can be set up to 1,000. And again, typically we see like all these limits within 1,000. So this seems to be okay. But what would happen is that you might end up with an over-filtering problem when you had a where clause in it, which again, we'll spend a lot of time on. So the point is that with pgvector 0.8, this parameter is more forgiving. Previously you'd have to set your EF search equal to your limit. Not true with 0.8, but we'll talk about that a little bit more. So how do you build an HNSW index? So I have a new vector. I want to put it in here. I'm sorry, the background's really dark here. So basically what happens is that HNSW is in layers. You have very sparse top layers and then basically every vector in the bottom layer. And as you go through each layer, like you may or may not make a connection. In this case, we're gonna make it, this vector is gonna make a connection in each layer. It's gonna get denser. And then the bottom layer, you're gonna build out your connections up to your M max. Then when you query it, let's say a new vector comes in, I want to see like what's my nearest neighbor. You go to the top layer, there's something called like a root. There's a root you go into. You find the nearest neighbor there, you go down to the next layer, you find your nearest neighbor there, go down to the next layer, and then you find your nearest neighbor there, and then you're done. So it's actually like quite an efficient algorithm. You spend a lot more time building the index, but like when you do the search is actually really fast. Going one level deeper, what actually happens internally? This is actually, like, I actually think this is pretty cool. So first you maintain a list of vectors that you visited, because this is going to tell you when to exit. And then you're going to maintain an ordered list of candidates, because the better the candidate, that's going to be at the top of your search result. And as you're going through above the bottom layer, so the bottom layer is layer 0, everything else is layer 1+. You basically first search in like small radiuses in the top layer so you can converge quickly, and then you get to the bottom layer, and then you have like your big search to find like the best candidates. And what's interesting is like in practice, this ended up working very well. That, again, the original NSW paper wasn't like great in terms of getting you in the right neighborhood, at least very cheaply, but like HNSW gets you there like pretty quickly. So again, this is like trying to nerd out over internals, but this is the magical step. Now, I don't expect you to read this chart, but the one trade-off with HNSW is it has bad temporal locality. So temporal locality is this concept in database memory, is that your most frequently accessed data is going to remain in memory. So that's why index lookups are hot, because you're typically accessing the same portion of the index and not as much as like the root of it. The temporal locality for HNSW is not great, particularly because these are like very large indexes. And when you have only like 6% of like a million vectors and you're doing most of your search in the bottom layer, it means that unless you've dedicated your database or your memory pool to your vector search, you're often going to be going down to disk. So your IO utilization, your disk setup is going to play an important factor here. That being said, you're still going to get a better search overall in terms of performance and recall when doing that. But this is something like, this is something that comes up. It's like, hey, my vector search is slow. Well, gee, you're using like a T4G micro with no memory to do the vector search. Like you gotta upsize. Like, and this is the thing, like to be cognizant of. Other fun facts. So M has a big impact on query time, because your M is, again, your number of links around you. And if you have more links, you're gonna have to search more vectors. And again, it might converge faster, but you're still searching more vectors. But the one thing I want to call out here is notice that these are the embedding models here, these names. Notice like 1 million, 1 million, 1 million, 5 million, 10 million. We're basically searching the same amount of vectors at this level. And we might see a little bit more divergence as we expand EF search, but this is like the point I want to make is that it's the embedding model that actually does the most to impact the number of vectors you have to search. This is something that I think often gets missed. But this is also really cool too, is that it doesn't matter like how big my data set is. I'm still like scanning roughly the same amount of vectors for that particular embedding model. And again, like it goes up logarithmically as it gets better, as it gets bigger. But this is like, I don't know, this is pretty cool. So the other thing to point out is as we increase M, this is what I was talking about. Like as you increase M, you're going to have to scan more vectors just because like there's more bidirectional links. So you want to be careful with setting M, because if you do want a higher recall search, you will get that. It's just going to cost more. And again, this is the cost performance trade-off. So, and again, this is also showing like the embedding model. So in this case, the embedding model impacts it as well as these are two different embedding models. And again, what's interesting here is also this is like less dimensions, and yet we're scanning more vectors because of that embedding model. All right. Index build speed. So with HNSW, you want to spend more time building your index. Why? Because the more time you spend building your index, the faster you're going to be able to get your search. Now, at some point, there's a diminishing return with pgvector's implementation. Like you get crank up your EF construction, but you're only going to get like so much more recall out of that. So recall is the top here. And notice like we're just kind of going up, this is a serial build. We went from like 1 hour to 3 hours. Okay, so like this is a diminishing return. But what's nice is with parallel workers, so this was using 64 parallel workers, again, like we're still, degrading in performance in the same degree, but the difference is that this is minutes. So parallelism is important here if you have your entire data set, available. Plus the fact that like I'm able to get that recall bump, while spending much less time building it. Again, the trade-off was like I was using like a 64 core machine to build this. Like that's it's a fairly powerful machine. But the point being that if I can spend more time building the index, I can get a better quality search. Now, this is the slide that like made me blink because initially, I was making the recommendation on EF construction 256 based upon this. And then I started running some more tests. And I noticed that even though recall got better, the yellow line, my query performance started going down after EF construction 64 because what ended up happening is that it started scanning like some more vectors, and there was enough vectors to impact convergence on the scan that we weren't getting as good performance. And again, this is like a minor blip, right? Like this is within 10%. So it might be worth that trade-off to make sure that you are eking out the best possible recall. Now, on the flip side, based on the scale you're running at, that 10% may matter. So you have to just, again, that's ultimately the trade-off you have to decide. And so you probably notice here the recall is bad. Like this is the just 960 data set. It's just, I talk about vectors as a nasty data type. This is just like a nasty data set to test against. Like it's really hard to get good recall. Oop. All right. So last bit. I think, okay, this is just to show that actually with the just data set, you can get like 90% recall, but you have to really crank M up. And the trade-off is that it takes longer to build the index. Your search will ultimately be slower, but you can get good recall. Now, we've talked a lot about building the indexes, but we also need to load the data. Because some of you may have data that is already, you have all your data available. You just like load it into Postgres. You use HS, you create index, build with parallel workers, you're good. But you might also just be loading it iteratively. And there actually is like an interesting toe stubbing thing here, which we're going to look at, which is if the ingestion method you pick can actually significantly impact performance. I think the best way to show this is with a chart. So here I'm trying to insert 1,100 dimensional vectors on a fairly beefy machine. And again, this was just like single insert. If I inserted them one at a time, it took about 25 minutes. If I used a bulk insert, so that's when you do insert into table values and you put like a bunch of the values in it. See, it got a lot faster. And then there's copy and copy binary. We'll talk about copy binary in a second because we're going to see like, wait, copy binary is way faster than copy. So copy is a mechanism in Postgres to quickly ingest data, particularly you're reading it from like a stream. And copy binary is using the Postgres binary protocol. So these are probably things you never had to think about. Like I honestly never thought about copy binary until vector search. But the reason is it has to do with the transformation. So typically when you have your vector, like your LangChain or your source application, it's in a binary format. Now, if you just do things by default, what's going to happen is Postgres is going to take the binary vector, or your driver is going to take the binary vector, translate it into text, send it over the wire, and then have to translate it back to a binary. And again, normally you don't notice this because your payloads are so small. But with a 1,500 dimensional vector, what's happening is that your What's happening is that you're taking this 1,500 dimensional vector, so 1,500 4-byte floats, converting them to ASCII, sending them over the wire, and then taking them from ASCII and converting them back to binary. And I can tell you it's expensive because I recall like looking at my, seeing this like really slow test. I'm looking at my database and like the CPU utilization wasn't maxed out. I went to my client and the client was maxed out. So it was like, it was kind of like a revelation. But if you switch to the binary mode, which, there we go. So if you switch to the binary mode, you don't do any conversion. You just send it over the wire and it goes to Postgres. So this is like a real issue because we've seen folks in the pgvector repo saying like, oh, like this is so slow, and it's like a workload that I could run in a minute on my laptop, and it's because of that. The other thing is, if you really, if you have a lot of vectors coming in, you might want to add some concurrency to it, so multiple clients inserting. And what's interesting is that you're gonna like copy is like really awesome. You can see that like very quickly you can get very good copy results without having to use more clients, particularly on newer versions of Postgres. Bulk inserts are pretty good too. You can see that with like this bulk insert 1,000, there's eventually diminishing returns. But obviously you can see that if you are doing iterative inserts, because you might not be able to do bulk inserts, the more concurrency you throw at it, the faster you can get, but likely you're saturating all your connections on that. Finally, the best method is if you can preload all of your vectors and then run create index on it, which is what I did here. That is going to beat everything of this, because like that method is really good. Caveat emptor. There's currently, you need to make sure you have enough maintenance work mem for the create index to fit in memory. Now, if it doesn't fit into memory, it'll spill to disk and it will continue the index build, but it gets like significantly slower. Like it could be like an order of magnitude slower. So this is where sometimes some of the index building strategies today in pgvector might involve like partitioning your data and building like smaller indexes around it, which we'll talk about in filtering. So,
a quick question. Bulk insert is like the single insert statement with like a whole bunch of values in it, or just like a bunch of inserts in one transaction?
Yeah.
In one insert statement, right?
Yes.
Okay.
Yes.
Sure.
Yeah, I should have made an example for that. Good feedback. All right. So best practices for building HNSW indexes. So start with the defaults. Like I've seen a lot of examples where people try some values that are not the defaults, and they're like, hey, this is like I'm getting like bad performance, or I don't understand what's going on. Like the defaults actually work really well. Like we've tested them at like billion scale, and we've seen like really good, some really good results. If you need to like truly maximize all performance, make sure you're using plain storage for the tables. The trade-off is that you can only fit so much data into that particular row, but that you have to determine what's best for you there. So for ingestion, if you can just like reload your data and do a parallel build, that'll be the best. If you can't, if you have to use an iterative method, either bulk the inserts or use copy binary. Now, one other thing, quantization can help reduce storage. So what's this quantization thing? So quantization is a technique where effectively it's a trade-off between having a smaller vector size and losing information. So there's three methods typically used with vector search: scalar quantization, product quantization, binary quantization. We're not going to talk about product quantization. Scalar quantization is saying I'm going from like a 4-byte float to a 2-byte float, or a 4-byte float to an unsigned integer byte. Whereas binary quantization is I'm going from a 4-byte float to a 1-bit integer. So one of these loses a ton of information and only really works for like a very select distinct use case. The other was interesting is that the 2-byte float could actually be a way that you might just want to use it by default, in your vector indexes, particularly if they get big, and we'll see why in a second. So here's how you effectively do scalar quantization with pgvector. So Postgres has a feature called expression indexes. Who's familiar with expression indexes? Cool. Expression indexes are awesome because basically if you have an immutable function, so an immutable function is one where if you give the same input, you always get the same output no matter what. You can put it in as part of your index. So like a common use case is if you need a case insensitive search, you take like a name and put it to upper, or you put it to lower. Like I don't know if you're an uppercase or lowercase person, but basically you don't have to store, you don't have to store like an uppercase column in your table. You just map it directly to your index and do the search on that. So scalar quantization, effectively, you can store your original vector in the table and install the reduced vector in the index. Like particularly if you need to do like some kind of re-ranking after the fact. You could even choose to store like your every vector as a half vector, longer topic. So binary quantization is very similar. Like again, you're going to basically take your original vector and store it as this bit vector. The thing with binary quantization is you need to do a re-ranking. Now, you might see other vector search options where you can basically, there might be API calls that do the re-ranking, or they do it automatically. With SQL, you can do all these things, right? SQL is Turing complete. Please keep me honest there. But like SQL, you can do pretty much anything. And the re-rank is effectively a kind of subselect that you do on it. So, SQL is magical. I love SQL. I understand there's it probably took me 10 years to figure out I could do that, by the way. But that's why I want to put this up here so you could see how you would effectively use it. Now, again, binary quantization has all sorts of trade-offs. One of the trade-offs is that you have a smaller index, which might not be a trade-off. That might be magical. And the smaller indexes are faster to build. But remember, it's all intention. So recall, if we start with our default EF search equals 40, we actually see for this particular data set, we don't lose too much relevancy between our original vectors and our 2-byte floating point vectors. But definitely for the binary vectors, even with the re-rank, we lost a lot of recall. And again, this is the whole look, this is so much faster, but yeah, we're only getting 80% recall, which might be fine. That might be 100% fine for what you're doing, but you have to measure it and make sure that's what you want. Now, what's interesting on the other end is once we got the EF search larger, we can see that our binary re-rank is not too far behind the other two, and we're getting better performance. So again, that could be something that works for your workload, and suddenly you significantly reduce the size of your vectors. Now, what's going to happen over time though is this might seem magical, maybe you make everything a half vec in your index, maybe you use binary quantization, but the problem is as your data set grows and you've lost information, you're going to have more vectors that look the same, which means in order to get better recall, you have to search over a wider set of vectors. So that's something to consider, because a lot of folks have been saying binary quantization is the best thing since sliced bread. You can use it to use it for these very large vectors coming from these embedding models. But if your data set gets too big, it's not necessarily going to work. Maybe you can partition it. Maybe there's some things you could do with filtering to maximize it. But you need to make sure that you have enough bit diversity to make sure you can make the appropriate determination between the distances all around you. Speaking of partitioning, this gets us into filtering, which is the final topic for tonight. Filtering comes almost immediately after you start using vector search, because you inevitably will add this thing called the where clause. It's so frustrating. Why would we ever want to use conditions to narrow down to a smaller set of results? So the reason why this is a hot topic, because typically you see benchmarks and it's just on the general search. But no, ultimately, you have either I might be searching over a particular location and trying to filter on all these attributes and whatnot. And this has an impact on ANN. Now, Postgres may choose not to use the vector index, and we're actually going to see that's fine. Before pgvector 0.8, it was very confusing. Now it's fine. But the other thing is, the problem before pgvector 0.8 was that we'd see a problem with overfiltering, where we do a search on the vector index, and then the filters would apply, but they were too selective. So you'd get 0 rows back, even though you should be getting the full 10 back. And the filtering would also occur after using the index, so it might end up being slower. I just want to point that out because people talk about pre-filtering and post-filtering. Honestly, in some ways it doesn't matter, but we'll talk about that. So what is it what do you have to decide in terms of filtering? Because this is actually this is really about your indexing strategy. So first, query patterns. How many filtered queries do you have versus unfiltered? So unfiltered was just what we've been looking at the entire time. Select star from table, order by limit. Filters with the where clause. And again, this matters. If you have all unfiltered queries, you're going to use an HNSW index. If you have all filtered queries, depending on your filters, you might not use a vector index. You can also use both at the same time, and that's the pgvector 0.8 feature, because Postgres will make the best selection for you. The biggest thing is selectivity, which we're going to talk about on. And again, for my first 18 years of using Postgres, I don't think I even thought about selectivity. But I was typically using primary key lookups. High selectivity is going to be the most important thing as we look at this, and we're seeing an example of that. But also what's going to impact is the number of vector distance comparisons per query, because that is going to factor into the selectivity math. So first, let's talk about selectivity. So imagine this is our table, which is this blending in purple block. So selectivity is a measurement of how much of the data you're eliminating with your filter. So this is an example of something that's lowly selective. So if my filter only removes 25% of the data, that's not very selective. And typically what will happen in this case is that Postgres will choose not to use an index. It's going to choose to do a full table scan because that's going to end up being faster. Which is like, wait a second, what? But it's because, a vector index effectively is going to have to like randomly look through the table ultimately. Whereas a full table scan, like there's some optimizations to like quickly scan everything, parallel workers to be able to pull this result. So as you get your selectivity numbers smaller, you're actually being more selective. So this is higher selectivity. And typically, if you're at, this is like 0.25% selectivity, this is typically where you might see a B-tree index being used because you're looking over such a small set of data that you're able to scan it very quickly with that index and it'll pull out that result. So we have to think about that percentage, and we have to think about how fast it is to do those 5,000 operations. So remember that we can scan about 5,000 vectors that are, let's say, 512 dimensions in 2 milliseconds. Cool, because that's ultimately going to be like our factor in terms of throughput. And when we think about selectivity, we say like if I have 10,000 vectors in my data set and my selectivity is 1%, that's going to be 100 vectors, which means it's going to take a fraction of that to be able to scan them. And this is going to matter for index selection when you start doing the math. So before pgvector 08, you basically had two filtering strategies. One, well, actually the first strategy would be YOLO, which is you just build a vector index or not and see what happens. The next strategy was building partial indexes, where if you knew that you had a filter that was commonly used, you could add a where clause to your index, and basically you'd only index those vectors matching the filter. And then there's partitioning, where again, you can basically, if you knew what your filter was, you could partition the data into like smaller sets and build an index on this. This all has trade-offs for a lot of different reasons. Effectively, because if you like do too many of these things, you're going to spend a lot of time wasting query plan to figure out which partition to go to, and that in itself can take time. That being said, we've seen people use both of these very effective at scale, like billion plus vector scale in Postgres. So these methods do work. It just requires a little bit more management. But with pgvector 08, the goal is to make this more magical. And this really actually starts from something I think is very technical, which is cost estimation. So Postgres uses something called a cost-based optimizer, where basically it looks at all these different stats and says like, hey, I need to scan 10,000 rows, using this method to perform the query, or this one's 100,000 rows, so I probably want to use the 10,000 row one. Up until pgvector 08, the cost estimate of doing an HNSW scan was grossly underestimated. Effectively, it was a constant, basically. With pgvector 08, it actually has a mathematical formula to say like, oh, based upon the overall size of your data set and your M and E of construction, a few other things, I know that I'm going to scan about, let's say 3,000 vectors. And because of that, it makes it possible to be used with other indexes and make the better choice. This allowed to add this feature called an iterative scan. And the main thing with the iterative scan was to solve the overfiltering problem, which we'll see in great detail in a second. So remember, overfiltering was, I look at my vector index, I return 100 rows, but my filters eliminate all those rows, and then I get no data back. Like that's a bad experience. There's a parameter, it's turned off by default, so you have to explicitly set it on. And it's called, this HNSW iterative scan. So 3 settings. Default is off. Strict order means it's going to return it in the exact order in terms of the overall results. And then there's relaxed order, which actually returns better recall, but you might need to do a final re-ranking on it. I know it's kind of weird because remember, recall is not accuracy, so you might have to do a little bit more work there. All right, so this is so I'm going to apologize. The next few slides are a lot of tables. This is the part I'm trying to get the presentation a little bit better. But the way I want to set it up is that you have this table, create table embeddings, and these are filters of different selectivity. So these are like 10% selective. So I think it's like numbers 1 through 10 here, 1 through 100, 1 through 1,000, 1 through 10,000. And through this test, we're going to see how these different filters apply as we improve our selectivity. So remember, this is like low selectivity, this is high selectivity. So in this case, we're doing a regular like select star from table where filter equals, so this is where filter 10 is set, where filter 1 is set, et cetera, et cetera. So this is just the defaults, pre-pgvector 08. We can see that, QPS doesn't matter here, but we can see the average number of rows returned, which is, as we get more highly selective, we're not returning any rows. This is that bad overfiltering experience. So what has changed? So before pgvector 008, what you would do to solve the overfiltering experience is that you'd expand EF search to the max. And again, it solves part of the problem, which is I get enough rows back, but here our QPS is not as good. Like it's a 20x fall off, which is not great, but hey, at least you're getting results. And if we're highly selective, which is we eliminate a lot of the rows, like we're still not getting enough results back. So a lot of the complaint was that pgvector is slow and I'm not getting enough results back. So the change in pgvector 8, which is that iterative scan parameter, so we're using relaxed order here because we get the better recall. We can see that now with our when we have low selectivity, we're getting all the rows back that we want pretty much, and we're getting much better throughput overall. Now, there's also this drop off at the end. You can see that when we're highly selective, we're still not getting enough rows back, and our QPS is even worse than before. But again, if we're not getting enough rows back, QPS doesn't even matter at that point. So what's going on here? Like why does this matter? So the way the iterative scan works is that basically it's going to keep searching the HNSW index until it either finds enough rows to satisfy the limit, or it hits that max 2000, which is what's happening in this final case. Now, the reason it works well for low selectivity is that there's more rows in the index that match the filter, so the probability of getting all your results back is much higher. But if you're highly selective, that means there's very few rows in your graph around you that are going to match that filter. So you have to search more and more and more of the index to the point where it's probably better to do something else. I can tell you in that case, it's better to do something else. You can use a classic B tree. So the B tree is your standard create index on embeddings, whatever the value is. Now, this is still like classic index theory. If you have low selectivity, so again, you're searching like a large chunk of the table, it's much faster to do a full table scan. Like you're not like the index is not going to give you anything here, or the B tree index won't give you anything here. But as you get highly selective, meaning that you have less rows that match the filters, look at that. Like we're like beating like all the results from like the rest of it, and this is really cool. It's basically saying like if you know your filters and you don't and that they're they're going to eliminate most of the rows, don't use a vector index. Use a B tree. This has been like a lot of my conversations over the past few months with people. When they're like, "Oh, I'm trying to build this vector index, and how should I plan it?" I ask, "Well, like, what are you storing?" It's like, "Oh, I have like 300 vectors per customer, whatever it is." I'm like, just use a B tree. Like, you're going to be like much happier for a lot of reasons. But it gets better. So imagine if you have two filters. If you have two filters, you're even more selective, right? You're basically applying like 10% to 1% and 10% to 0.1%. Actually, that's wrong. It really should be times, but my fault. So there's actually multiple ways to do multiple filters. You do a multi-column B tree, which is great because you get all your rows back and it's super fast. Or a lot of what we see now is like people have JSON in their Postgres, and then you can actually use a gin index on your JSON and like apply multiple filters on it. And both methods work, right? Like if you always know you're filtering on these two columns, you probably want to use a multi-column B tree. And like, look, it's like 1100 QPS in this example, which is like way better than even the other one. And again, if you're not exactly sure what you're going to be filtering on, it could vary. So there's different schools of thought with like using JSON and Postgres. And I, for one, have kept JSON in my Postgres databases. And I can tell you, like, I've now actually told folks, like, for this particular use case, like, yes, like, instead of having like 50 columns and you don't know exactly how your selectivity is, put them in one JSON column, put a gin index on it. Like, yeah, maybe you're not as fast as like some of these other methods, but like you'll be consistent and you'll get enough rows back. And here's the kicker. If you know that you don't need the vector index, don't use it. Why? These other indexes are like a fraction of the size. So if you know you're mostly doing like filter queries on it, like use those. That's the takeaway. Don't use the vector index. I like vector indexing has been like my passion project for like the past 2.5 years. And here I'm telling you, saying like, don't use that. All that was for nothing. Like use these indexes. But that's true, right? Because if you know that you have low selectivity, you probably do want to use the vector index here. So best practices for filtering. This is like my favorite thing. If you don't need a vector index, don't use it. There's plenty of other indexing, methods for it. Again, I talked to a customer where they're like, well, first we need to filter on our biggest filter is first on location, and then it's on a range, and then we're doing some things where we need to compare vectors. But it's we built this vector index and it's slow. I'm like, you just told me you eliminated most of the rows without it. Use those. So don't use the vector index. And because at the end of the day, if you think back to how long it takes to compute the vector, we're doing 5,000 of these vectors within 5 milliseconds. You can do a lot of computations per second there, and it's probably going to be good enough for your use case. So the other thing too is you can also leverage partitioning and partial indexes based upon how much data you have, what your overall strategy is, and you can mix and match. That's part of the fun. So that being said, this is still not. So that being said, there's still work to do in terms of the indexing. I think the big thing that's emerging now is you might hear it in terms of index-based pre-filtering. So imagine that you have a data set that it might still be highly selective. You might have that 0.01% selectivity, but you have, let's say 10 billion rows. And even with that high selectivity, that's still going to be, what is it, 1 million, you have to look through 1 million vectors or whatever, 100,000 vectors. It's going to be enough where it's going to be hey, these queries are kind of slow. So there's a case for doing more of the filtering as you're scanning the index. This is an area of active research. There, at one point there was a new paper per week talking about how to do this. And I think, part of pgvector's take is the pgvector promise is once something's in the binary format, we want to keep that, we want to make it so you don't have to rebuild your index every single release. If more things are added, it'd be iterative. So, keeping an eye on the index-based pre-filtering methods, will there be one? I can't say yes or no. I would say it's likely at some point, but it's just keeping an eye in terms of how the research stabilizes. There likely will be, additional, vector data types. There is an open path for some of these, so please test. And there's actually some newer things in Postgres that can help speed up vector search. I think, the other thing, I actually happened to meet up with Andrew Kane, who's the lead pgvector maintainer this week. And we talked about, possibly a tiny optimization of effectively adding 8 bytes per row, but it would eliminate one of the computational operations. So it's probably a worthy trade-off, but we'll see. So conclusion, we went from hey, here's the use cases to hey, here's Postgres. It's kind of cool to here's some best practices and all the mathematical proof that justifies the best practices. So this is a lot of information, I know. I'm glad Jeremy's recording it. But if we really want to boil it down simply in terms of what to do, first is when you're bringing in a vector search, regardless if it's Postgres or anything else, into your generative AI application, you're going to have to choose between your query performance and recall. Those are the two trade-offs. You want better recall, you're going to take a hit on query performance. You want better query performance, you're going to take a hit on recall, and that's fine. That's the tension. Choose what you want. Choose what makes the most sense for your system. And look, and there's always ways to help improve it, right? The Postgres answer is you need more throughput, add a replica, send read traffic there. You need even more throughput, add another replica, send more read traffic there, scale it up. There's all sorts of different levers. And that's really where you need to determine where you want to invest. Is it going to be your storage? Is it your compute? Is it your indexing strategy? And again, the indexing strategy, one of the takeaways I want to have is that, based upon your query pattern, you might not use a vector index and that's completely fine, or you may use a vector index and that's completely fine. But again, these all have trade-offs. So what's interesting is this last statement. I had to originally say pgvector is rapidly innovating, and I switched it to pgvector continues to innovate. Because what's interesting is that it seems like the pace of innovation around vector search is slowing a bit, in my opinion. And that's a good thing. It's because the technologies have matured and they're stabilized. And you still should do some planning for today and tomorrow, because Postgres itself continues to evolve. pgvector itself will continue to evolve. And again, all those things are fine. But we understand the search domain much better now. And it seems a lot of the work and most of the conversation that I have around this is that we want the vector search to be the boring part of this. We don't have to think about it. We need to think about all these other things that go into building the generative AI application. The prompt design is really going to be the biggest impact in terms of the results you have. Oh, and yeah, you have to link all those other data sources together to do your traditional SQL and other queries. But that being said, generative AI itself is still rapidly innovating, so you do need to plan for today and tomorrow. And some of that might impact your schema design, like if you need to swap an embedding model out, it's a different dimension size, and so on and so forth. So with that, it is 7:56. I know, well, I don't know if you consider that late here in Seattle. I mean, New York, that's like when we're just getting started. So thank you so much, and happy to take any questions.
I was curious, you talked about partitioning a little bit, but can you say a bit more about what people have seen partitioning?
Yeah, so I've seen multiple partitioning strategies. Again, it depends on use case. So first, the one to be most careful of is hash-based partitioning. So a hash-based partitioning strategy, one might joke, means you don't have any partitioning strategy, but like really it's primarily for load balancing. And the problem is if you have filters, you might actually end up into that over-filtering situation where you might be in a partition that doesn't have enough of the candidates that you're seeing, and you end up not returning enough results. But there's been a few kinds of partitioning I've seen. Like first, it's definitely that does happen. The hash-based one, when you have just like too much data. I've seen ones where it's been partitioned by the embedding model you're using, so that way you have all the vectors of a particular dimension in one partition, and you route to that. And I've seen hierarchical partitions as well, where depending on what the partition key is, like some it might be like time-based, so all of the vectors created at a certain period are in here, or it might be like account-based, time-based, etc. Some mix and match of that. The thing to keep in mind is you want to, like for pre-pgvector 08, you really want to make sure that your filters are within the partition as much as possible, so that way you're always returning enough results. The twist with the new version of pgvector is that it matters a little bit less because of the iterative scan you can go through, but it can still matter because if you're highly selective, you could still end up over filtering in that case. But if the additional filters on the scan are just it doesn't do enough to impact the filtering, it may be fine. I guess the final bit, there's one case I saw when I first told about it, I was kind of like, but like I saw it working. I was like, oh wow, it actually worked. It was a mix of partitioning and postural indexing. So a lot of partitions, and within the partitions, a lot of partial indexes. And again, the person I talked to, they built out all of the necessary automation and management around it. And this was something I forget how many billions of vectors it was. It was some gigantic data set. But it worked. I was surprised. The planning times are good. There wasn't that much lock contention. So a good design does help, but that is a lot to manage. There's a lot of maintenance overhead there.
Can you explain a bit more how the B-tree indexes will work on vectors? Wouldn't it have to be an exact match?
No. So the B-tree index is not on the vector itself, it's on some other keys. So it's going to be on an integer or something like that. And what happens is at the end, you do the ranking on the vectors at the end, because you fetch the vectors from the heap and do the final ranking. But this is where the things about plain storage and all of that come in, because it's going to be one, that itself will be a faster operation, but also because if you can eliminate down to 100 rows and then you're just doing an ordering 100 rows, it's very fast.
So it's you have a bunch of sort of attributes stored within the vector.
Yeah.
And you're searching out the attributes.
Yeah, so I can just bring it back 1 second. All right, so because you have the table, so the vector's in the table, and then you have the attributes in the table. So you build the index on the attributes, and the final search is on the vector.
Because we spoke about vector indexes and B-tree indexes together. It makes sense.
Okay.
You talked about optimizing vectors and how you have to make sure you don't run out of diversity.
Mm-hmm.
How would you know that you're running out of diversity?
So one way you can get that is through your general measurement of recall. But let's take I think the best way to look at it is looking at the binary quantization, because this is where it impacts it comes first, right? So we only have ones and zeros to be able to capture the vector, right? And in this case, the binary quantized function in pgvector basically says, are you positive, you're a 1, if you're negative, you're a 0. So imagine I have a vector data. Well, here's a simple example. So the SIFT 120 data set, every integer is positive. which means like if I use the binary quantize function, like everything's gonna be 1. So like there's gonna be 0 diversity. Whereas something like a 1500 dimensional vector, that kind of where you might have like mix of positive, negative, you're more likely to not conflict because there's going to be more diversity in those bits. So there's different strategies for doing binary quantization too. There's like statistical binary quantization, which like helps to avoid that problem with like the basic binary quantization because it looks at your data set and then it can determine like, oh, here's like a center, do the comparison against the sender, and you actually can't get better recall that way. While trying to like do that as an inline function for pgvector, I discovered that there was actually funny thing, you couldn't actually toast the function definition where you might have a very large value in it, which I think might be fixed in PG18. I have to double check on that. So the reason I mentioned that is that if you want to like experiment on it, like with like statistical binary quantization, it might not work out of the box just yet. You'd have to like write your own like C function to be able to do that. So long story short is, really the best way to see it outside of this example is like it's over here because here's like a million vectors and and we can see that compared to the original vectors versus the binary vectors, like the recall is lower.
So it's just you measure your recall. I mean, there's no way to visualize the diversity or the uniformity of your actual vector space.
Yeah, I mean you could build a tool to do that.
Okay.
And there might be tools that do that as well.
I was wondering why there's so much emphasis on the time needed for indexing. Can it be done after like work hours, like with background or something?
Okay, up to you.
Okay.
But again, depends on the overall data set. Like I built one, I was able to do this entirely in memory. I did like 1 billion 120 dimensional vectors. It took, I want to say like 2.5 days.
Oh, yikes. That will work.
Yeah, that's what I'm saying. It depends. It all depends, right?
Also, if you're inserting more vectors or inserting more rows, you have to rebuild the indexes. Right?
So IVF flat you do, HNSW you don't. So yeah, so HNSW is iterative. So the nice thing about HNSW is like as you add more vectors, like it's almost like a regular tree in a way, like it's a graph, but as you go through, you can basically iterate, and like as you add more, you just expand the graph. IVF flat, what'll happen over time is if you insert more vectors, your centers start to skew, so you're going to start getting worse results as you do more queries. So for that one, you need to rebuild over time.
Even here, wouldn't the hierarchy change? Like if my lowest level vector belongs to a certain part of the tree, and then I insert I guess it would stay in the same part of the tree.
Yeah. So what happens is that you'll build, you'll build your bidirectional links between the appropriate neighbors. Now you do raise a point, which is that as it does get larger, like the iterative graph you're building might not be the best possible graph. Like you might want to rebuild, but the degradation has generally been slower, at least from what I've seen. But what's interesting is like we've seen things get to like pretty large scale, and they're still like maintaining like a very good level of recall. Oh, but no, good question.
When people are worrying about like the index build time, is it usually like that they want it in hours and it's like stretching it in days, or are there some cases where they like want it happening in minutes?
Yeah.
Like, your real-time results or
Yeah, so-
constant updates.
Yeah, so this came up a few times in a real use case. So let's say, I'm trying to anonymize it. So let's say you have a business where you're billing by the hour and you can build very rapidly by the hour. And in order to do that, like, let's say it's built upon like an ingestion of data that comes in. So you have like, 2 million items that come in and you need them like ingested as quickly as possible because like, you're billing by the hour, and like, the sooner you start billing, like, the faster you're able to make money on that. This came up in like some real use cases where it's like we need to be able to do this efficient search like very quickly, but if it takes 8 hours, like there's 8 hours of productivity lost. If we get down to like 10 minutes, like cool, like we're ready to go.
Yeah, that is, like there's some use cases where people really are trying to get the indexes to happen in minutes.
Yeah, but I think part of it too was just like it was very specific to pgvector that when HNSW was introduced, it was slow. And then, I have a slide that shows like how much it like sped up over time. Like there's a clickbaitish blog post. I was like, here's the 150x performance speed up in pgvector, which is basically comparing like the original HSW build to like the binary quantized one. So like that was the clickbait part. But even like the regular build without the binary quantization was like 30x faster over like the span of 9 months.
Notice you have like a 16x machine for most of your results.
Yeah.
For 1 million, 5 million data sets. So
Yeah.
it seems like a huge amount of resources to provision for those small data sets.
Yeah. I want the CPUs.
Is it really used or is it just?
CPUs get, oh yeah, for the index build, the CPUs are definitely used. Like you will saturate your CPU if you're doing like a very intensive build.
From memory purposes, you really don't need such a.
For these ones, no. For the billion scale data set I was talking about, I think I used like an X2 IEDN. I want to say 32x large maybe or 16x large. I can't remember. It just again, that one I needed the memory. So like yeah, but yeah. So for this, the reason I was choosing those machines was primarily CPUs, and then for some of like the it was mostly like it was guaranteeing like I could have as much in memory as possible, but like it was over provision for that.
I have one more threshold. Sorry, do you have one more?
Yeah, I have one more different topic, but you mentioned about pgvector roadmap and planning. How do you guys plan that? Is there a meter of that plan or?
Just chatting, GitHub issues, meeting up. I met up with Andrew this week, and like part of it is like sharing. I think a lot of what helps is like understanding real world cases. Like quickly after we saw pgvector and more widely available, we saw like the index build speed does matter, but really first like query performance matters. Like people are trying to bring real world things here, but okay, now they're starting to do that, but they're adding like tons of vectors to it. We need to speed up build speed. Okay, like storage is too much. We need to quantize it. Okay, like everyone adds a where clause immediately. We need to be able to get better at filtering or give better options. Like those are all came from like just real world situations.
Building on that, I guess it does depend on what you're trying to do, but can you give some more examples of use cases where people might use pgvector over like Pinecone or purpose-built vector DBs?
Yeah, so I think a lot of it is there's a lot of different reasons. The first thing we see is that people just want to use the tools they're familiar with, and like a lot of their tooling is built around Postgres, so it's a natural extension to use Postgres for that. Also, data locality. In this case, if my source data and my target data are within the same database, it's easier for me to access it. Or based upon like the application, the vector might be tightly tied to that. And that's most often what we see, but a lot of it does come, and I do have like my experience being an app developer, a lot of it just like I have my tooling already set up, I don't want to learn anything else, let me do this. And it's simpler to manage like one system that's, the same as what you're using versus like a whole bunch of systems. But I think, the thing, I really don't want to like get into comparing like specialized, vector databases, but what you actually have been seeing in a lot of those is that, they build out, these vector features and they're starting to add like traditional database features, things like, some of them are still like added feature indexes. I'm like, okay. And, of course, my favorite like things like having backups and, availability and durability models, et cetera. Like, again, you see that you've reinvented a lot of things that if you look at databases that have been around for 30, 40 years, those are just table stakes. Like those are features that just work and are very well tested.
Can I get one more in?
Go for it.
It was another sort of threshold question. Like, so the threshold where, because I was listening and I feel like when you were talking about the threshold where it makes sense to start using the approximate nearest neighbor versus just looking back to B-trees and not even using the approximate searches. And it felt like, I'm just curious how you think about the threshold. It felt like I heard you say maybe in the hundreds of thousands of rows, you might start thinking about ANN, or maybe when you're measuring the size in gigabytes, but if it's kilobytes, you would probably just use a B-tree, or if it's just 1,000. Just what's the kind of ballpark range where you definitely use a B-tree, or you definitely use nearest neighbor? Yeah.
So I go back to this slide and notice if you recall from all the very mathy slides earlier on saying we're scanning at EF search equals 40, M equals 16, we're scanning 1,000 vectors, between 1,000 and 2,000 vectors per scan. So I actually think back to this. It's really, I should have done like 1,000 distance operations here to like actually align that, but then the numbers are too small. But I start thinking about that, and I start thinking about like the selectivity around that, because we know that it takes like for all of these less than, on average, less than a millisecond to return, to return 1,000 vectors or do 1,000 vector computations, and your QPS is then, 5 times that number. That gives a starting point, because we know that then, as our vector index grows, we're roughly going to be within this threshold. That being said, with the filters, if we know that we're going to be filtering down to like 1,000, and it's going to take less than a millisecond each, that's like that's really where that starting point comes from. I know I just like went in a circle there, but like I try to think in chunks of 1,000. And what I tell people is like, if your filters are returning about 5,000 of these operations, on average that's like 4 milliseconds. That's probably going to be fine for what you're doing, but if we're getting beyond that, then you probably want to start using the approximate nearest neighbor search. But the biggest factor is going to be the selectivity at the end of the day, because if your selectivity is low, you're basically going to return enough rows to satisfy your filter. Like the HNSW index is going to work very well. It's like as you get highly selective. This is
So
where you're
like this is 5,000 distance operations.
Yeah.
If my selectivity was that I returned 100 rows, am I having to do, is that like sort of like the n exclamation mark? Because I have to compare each of those rows to each other row. So is that like, how many distance operations is that?
100.
100, okay.
Yeah.
So 100 rows is 100.
Yeah.
Okay.
It's like 100 rows and my query vector.
Okay, okay.
My other answer is you could try it and see. Because in some ways, like for your workload, like you do need to try it and see.
So you don't compare the vector already within themselves. You will compare the query vector to all
Oh,
the
right,
vectors.
okay. Yeah, that makes sense.
So one question I have, like I'm seeing like there are so many things you need to know about, like, but then like how do you manage the issues that are working, like can manage the issues, think about that.
Yeah. So the good news is that I think the pgvector README like really condenses it down. You can read like some blog posts where that also showed like some of the best practices. This was about showing the best practices and the proof for how we got there, because that was part of it. Like I think if I really want to distill it down, like the things that you need to know is that these vectors tend to be larger, so you need to understand like what that means for your storage, and then how you're querying the data. Do you have a where clause or not? If you have no where clause, it's easy. You're going to use an HNSW index. If you have a where clause, then you have to think a little bit more in terms of like how much you're filtering down, because then a regular Postgres index might be good enough for that. But if you're not filtering down enough, then you might need to use one of these vector indexes. That's the 30-second summary of the entire talk.
It's like a decision tree kind of thing.
I'm sorry?
It's like a decision tree, like if you're
It-
using this to that.
Exactly. Maybe I'll do the decision tree next time.
Quick question. So if you actually find that like your bit diversity is actually like kind of getting more and more homogeneous, would you suggest then like going back and like revisiting your like chunking strategy for to address that, and basically kind of like starting from the ground up? Because sometimes like you start one way and you're like, okay, this is going to be diverse enough, and then you like as you proceed you find that like say there's more specificity of the particular topic, then do you go back and revisit your chunking strategy?
Yeah, you might need to. That's actually a very good question. Because I mean, there's a few ways to divide it up, right? Because you might be able to say that you might be able to find some other way to divide the data with the existing strategy, but like if you see that like it's really getting everything looks the same, then like 100% you have to change the chunking strategy. I have a separate talk that talks about some of the chunking strategy. Well, not a whole talk, but like 5 slides that talk about the different chunking strategies. But like particularly you might need to get more specific, or you might just need to tune like your minor tweaks to it.
Awesome, thank you.
Yeah.
My question was more just along the lines of like those different practices that you just mentioned.
So like I said again,
Yeah, just like what are some of those 5 like chunking strategies
Okay.
If you could,
Copy and paste the slide in.
I could
the way-
Slack you.
Yeah. So the way I divided it up last time. So there's fixed, structural, hierarchical, semantic. So fixed is typically what folks default to. Fixed chunking is basically like chunk like 300 tokens or whatever it is. But that doesn't that's really fast to get started, but doesn't actually like structure it. Structured chunking is I have some kind of structure already in the document that I can key off of. Like think like HTML paragraphs. Yeah. Hierarchical chunking is, I don't know, like I know the document has structure, I know this has structure, so let me give some rules around how to load the hierarchy and see if you can, match them. And semantic chunking is effectively like, hey, embedding model, like you can figure out the chunking strategy because you already understand like the meaning here. So I'm gonna like give you like a couple of parameters and like you're gonna do like a lot of additional work on it, but like you're smarter than me, like you figure out the chunking strategy. So semantic chunking typically does get the best results per, let's call it a research. But ultimately, like if you're gonna probably end up somewhere with structural and hierarchical because like from there, you probably know the meaning and you have enough domain knowledge to say like, hey, look at it in this way and get the meaning out of it. Any questions about Postgres in general? How the community works?
I am just kind of curious. Have you seen a lot less work go into full text search and more work go into semantic search like this?
In general,
In
in
the community?
Postgres. So that's a good question. There's actually been a lot of work on extensions that implement like the BM25 algorithm, and for like full text search. But in terms of vector search, there's been all sorts of different projects. I think pgvector's had the most adoption of them based upon what I've seen. And there's actually like not been all too many people working on pgvector. There's been a lot of excitement about using it in use cases, but it's not like there's been a ton of community resources poured into it. I think one of the discussions I'm planning to have in pgcomp.dev is a time to start like upstreaming more of the pgvector work into that. In terms of full text search, I do think like there's still work to do in Postgres and full text search, but one of the secrets is that the built-in tsearch2 algorithm actually works pretty well. I was talking to like some, actually multiple people the past month that are using it, and they're like, yeah, it's still like great after 20 years. It does, like depending on what you're doing, it does require some tuning, and like some of the tuning is a little esoteric, but for a lot of like the basic use cases, it works great. I used it once upon a time, but much smaller data set.
I'm curious if you've been following some of the purpose-built vector databases. Like, are they basically doing the same thing or doing something different? Or?
Yeah, so I followed it, or I do follow them. I have followed them. But yeah, again, I really don't want to get into like comparing like Postgres to like the other databases, but fundamentally, like most people implement some form of HNSW or IVF flat. Some people do disk ANN. I don't particularly also want to get into that one as much as well, but effectively, like things have been converged. Like it's all kind of convergent because like when you look at vector search, like vector search is just a feature, and then suddenly you realize when you have this feature and you're trying to build a database, you have to build all the other database features. And I think what you see is like, maybe like some have like different scaling properties, some have different durability properties. And like everything might have a purpose. Like that's in part why it was built. But again, depending on what you need, like you might find out you just need like all those traditional database features, and then you end up using Postgres.
All right.
Thank you.
Any more questions? Thank you.